Hey guys, welcome back to chapter 10. This is the last video for this module. Today we are going to talk about phase diagrams. So up until this point we have talked about phase changes, so solids, liquids, and gases. And this is one of the very first graphics that I put up for this chapter, right? So we know that there is a temperature component to these state changes. So we've got solid ice, we heat it up, it becomes a liquid. We've got water, liquid, we cool it down, it becomes a solid. So definitely there's this temperature piece to these state changes. But there's also a pressure piece. It's not just about temperature changes. We can also pressurize systems, and that can cause or prevent state changes from happening as well. So the last thing that we're going to do before we move forward from this chapter is just talk about something called a phase diagram, which takes into account this pressure and temperature all in one. So of a phase diagram, okay? We're going to talk about all the different parts of this phase diagram and just make sure you guys are familiar with each of them. So on every single phase diagram, there will always be a solid, a liquid, and a gas section. And for the most part, it reads like this from left to right. So solid, liquid, gas. Then we see these lines dividing the two states, right? So this line right here would represent the melting or the freezing, right? So it depends on which way you're going. So if we're going this way, that line represents melting. If we go this way, that line represents freezing. In the same manner here between liquid and gas, so if we go from liquid to gas, that's vaporization. If we go from gas to liquid, that's condensation. But this line is going to delineate that liquid-gas change. The other thing that we'll see down here is not all substances go straight from a solid, not all substances go from a solid through liquid to gas. There is this moment where we can change from solid to gas, skipping the liquid phase altogether. And there's actually a really popular substance that does this. We'll talk about that in just a little bit. But we've got this switch from solid to gas. And then there's a line that kind of demarks this as well. So going straight from a solid to gas is what we call sublimation. And then going straight from a gas to a solid is deposition. So just pointing out that that's another phase change that exists. And then last thing on the actual graph that I want to talk about, there's 2 points here. There's a triple point, so very unique place here. And let me go back and talk about these lines real quick. If I'm actually physically on this line, so if I get my little red pointer out here, and I'm physically on that line, I'm on that red dot, both states are present. I move a little bit to the left, solid, little bit to the right, liquid. But when I am on that line, that represents the state change. And remember, during a state change, both solid and liquid are present. Both states are present. So now back to this very unique dot in the middle here. This is what we call the triple point. So if we land ourselves right on this triple point, we'll see that all three phases are present. Solid and liquid and gas are all present at the same time. I've got a video later that shows this. Certainly is going to require some temperature and pressurization for this to happen. It's a unique point. But every substance has a triple point, so we can make it happen. And then we also have a critical point. So the critical point is where we have the liquid and gas are present. But then when we get past the critical point, things get fuzzy. So moving beyond the critical point here, we've got kind of both liquid and gas present, and they are kind of fuzzy where one starts and stops. So we call this supercritical fluid that's up here. So past the critical point, things get fuzzy. There's not a clear line anymore. Okay. So just familiarize yourself with those different points on the diagram. So now I'm going to depict a diagram for water, okay? As I alluded to, we've got both pressure and temperature that are factors in these phase changes. So if I look at the axes going from left to right, we've got our temperature increase, and going from the bottom to the top, we have our pressure increase. Okay. This is the phase diagram for water, okay? So we live right here at around 101 kilopascals of pressure, or if I used a different unit, this would be 1 atm of pressure. And what we see here is phase changes happen at a temperature that we're familiar with. So at kind of standard pressure, I come across, I see this line where phase is changing, and that happens at 0 degrees Celsius. That's not surprising to me. Staying in this standard pressure, I come across, I see another phase change, and that happens at 100 degrees Celsius. Again, that's not surprising to me. That's when water boils. Okay. But if I start to pressurize this system, so if I increase the pressure or if I decrease the pressure, what we'll see is these phase changes start to happen at different points. So let's say I jack the pressure way up. I pressurize that system. Now what we're going to see is this phase change from solid to liquid is going to happen below 0 degrees Celsius. So it's going to happen at a negative temperature. And if I have this like super pressurized system, I'm going to come a little bit below it. Now we see this phase change between liquid and gas happens at a much, much higher temperature. So we'd have to increase it way over 100 degrees Celsius in order to vaporize that water. So the pressurization would cause it to vaporize at a much different temperature. So just showing you here that pressure and temperature are very much a part of this equation. Ways that I'm going to test you guys on this, so I might pick a spot on the graph and I might say what phase or phases are present. I might say something like at 0.6 kilopascals, at what temperature, oh, that's kind of a silly one. Maybe I'll go above that. So at, 50 kilopascals, at what temperature does water boil? So you have to kind of find where 50 kilopascals might be, and you would say, oh, it's going to boil at around 70 degrees Celsius, something like that. So that's the way I'm going to test you on these. So here is the two examples of the points on the graph that I showed you. So here's an example of that supercritical fluid. So here we got liquid gas, and then we pressurize this and things start to get fuzzy. Is this a gas? Is this a liquid? It's kind of both. So there's one phase present here. The supercritical fluid application for that, this is what we use to decaffeinate coffee. So coffee is inherently caffeinated. But if we pressurize the system to this supercritical fluid, as we start to bring it back down and start to liquefy that coffee again, the caffeine particles evaporate off, but the coffee particles stay. So this is one of the ways that they decaffeinate coffee. It's also one of the ways that we extract hops in the beer making or whatever you're making process. It's one of the ways we extract hops as well. If you want to know more about that, it's really super interesting. If you want to know more about that, there's a lot more information in the book about that. And then also I've linked a video here for that triple point. So it's an experiment. You just kind of watch it and it'll show you where the three phases are present. So it's definitely a pressurized system. They start increasing the temperature. And you'll see the solid, you'll see a liquid, and then the liquid starts to boil And so all three are present there. The phase diagrams, I told you that there's a really, really popular substance that never enters the the liquid phase. So carbon dioxide. Carbon dioxide is what we know as dry ice. So have you ever seen dry ice before? Dry ice goes straight from a solid to a gas. It never passes through the liquid phase. That's why it's called dry ice, because it never gets wet, never gets liquid, right? So if we're looking at the phase diagram for carbon dioxide, typical standard pressure is somewhere down here, right? So if I look at the phase diagram for carbon dioxide, and I come here at standard pressure, we never go through the liquid phase, right? So we go straight from a solid to a gas or a gas to a solid. It never enters that liquid phase. We could force carbon dioxide to become a liquid. I've never seen it as a liquid, but I could force it to become a liquid if I super pressurize that system. Now at a fairly low temperature, I could see that carbon dioxide become a liquid. But down here at standard pressure, man, we never enter that liquid phase. So just kind of a cool application is something you're probably familiar with. Okay. Last thing I'm going to show you guys, this would be a good kind of indication of how I might test on a phase diagram. So I might say under the following conditions, which phase or phases are present. So at 20 degrees Celsius, 72.9 ATM. So we come here, 72.9. And then roughly 20 degrees Celsius somewhere in here. What phase would be present? We would be in the liquid phase. So just kind of an indication of how I might test on these phase diagrams. That is the end of Chapter 10 lectures. That is the end of the material for this first module. I hope you guys found these helpful.